In this note, we are going to be looking at some applications of derivatives, specifically how they relate to velocity and acceleration. We will even be looking into a second derivative and what that looks like in terms of our function and in terms of our graph. So before we do any type of examples, we are going to imagine that we have a distance formula. We'll be calling this S of t. So the first thing that you're going to notice is that we can find the instantaneous velocity, v of t, by finding the derivative of that distance formula. Now this goes on to further say that if we have our velocity formula, which remember was just our derivative of our distance formula, we can find the acceleration by taking the derivative. So what we have is acceleration is equal to the derivative of velocity, which was already the derivative of our distance. So acceleration is really just equal to the second derivative of our distance formula. So we would just take the derivative twice. So for example 1, a ball is dropped from a 100-meter tall building. The distance it has traveled is given by S of t is equal to 4.9 t squared, where t is the time in seconds. How long after the ball is dropped is it halfway to the ground? So the first thing that we need to notice is that the building is 100 meters tall. This is telling us that halfway is 50 meters. So our S of t is going to equal 50 in part A. So what we're going to have is 50 equals 4.9 t squared. I'm going to go ahead, divide both sides by 4.9. So 10.2 is equal to t squared. At this point, I am going to take the square root. Now, there really is no reason for me to do a plus minus here since I can't have a negative time. And I'm going to be getting a t of 3.2 seconds. So I've just added in a therefore statement here. It will take the ball 3.2 seconds to be halfway to the ground. The next question says, what is the velocity of the ball when it hits the ground? So before we can even do anything involving derivatives for this question, we need to figure out how long it takes for the ball to hit the ground. We know that the ball is the building is 100 meters tall, and so we are going to be doing the exact same thing as in question A, and we're going to be setting our S of t equal to 100. So our height, or our distance traveled, is going to be 100, which equals 4.9 t squared, and when I solve that, I'm going to be getting 20.408 is equal to t squared. I'm going to go ahead, take the square root of that, and I'm going to be getting approximately 4.5 seconds. Now that I know that, I can do my s prime of t. Now if you remember, the derivative of that distance function is going to be equal to my velocity function. So s prime of t is equal to, I'm going to go ahead and bring this squared down. So 4.9 times 2 is going to give me 9.8 t. And now that I have my velocity function, I can go ahead and I can plug in my 4.5 seconds that I solved for earlier. And this is going to give me my 44.1 meters per second for my velocity at 4.5 seconds. C, what is the ball's acceleration after 3 seconds? So I know from that beginning page that I had, acceleration, or a of t, is equal to the second derivative of my distance formula, or it's equal to the derivative of my velocity function. So we found on the previous page, so this is just like a quick recall, my v of t is equal to 9.8 t. That means that my derivative, or my acceleration, is equal to 9.8. Notice there is no t in here. This means that regardless of the time, the acceleration is 9.8, and if we're talking about units, it will be meters per second squared. If you haven't taken physics, meters per second squared is the unit that we're going to be using for acceleration, just like meters per second is the unit that we're going to be using for velocity. What you'll see in this series of graphs is a distance, velocity, and acceleration graph. This is just an image that I found. It's not the function that we were looking at previously. What you'll also find is that below I gave you these exact same graphs with some bubbles in there, and then below that even more are the solutions. So what I want you to do right now is just kind of take a look at these graphs, see if you're noticing anything. There are a lot of key points in here that I do want you to be paying attention to. Maybe see if you can see anything in common with any of these key features, I guess. Some of them are labeled on here for you. Others, you're going to have to maybe think a little bit harder about what's going on. But like I said, if you look below, you'll see some bubbles in there where I want you to put some actual terminology to use. And then below that are the solutions for you. Just a couple of notes that I wanted to make. So when an object stops, then its velocity is equal to 0. So if you notice, the question that I gave you asked for the velocity when the ball hit the ground. That is looking for the velocity as the ball hit the ground. But once the object has stopped, its velocity is 0. And the second thing is, when there is a constant velocity, then our acceleration is equal to 0. So if something is traveling at the exact same speed, not speeding up or slowing down, that means that the acceleration is 0. These may be especially tricky for those of you that didn't take physics. If you took physics, you're probably wondering why I'm even telling you this. And finally, the last thing that I wanted to point out is that when our acceleration is negative, or our a of t is less than 0, then we can say that the velocity is decreasing, or the object is slowing down. And if our acceleration is positive, or our a of t is greater than 0, then we can say that that velocity is increasing, or it is speeding up. Now you could notice these things, again, if you took physics or even just by looking at the graph, but I did think it was important that I just mentioned it for you here.